Hello IB18, it's David here again. I thought I'd make a small video just to follow up the Monty Hall problem, which you've been looking at. I always remember a conversation I had with Vicky Watson a couple of years ago, because she asked me about this problem. And she said, convince me that the answer's that you should always switch. And here's how I did it. I said, what's the probability that you win by switching? That's what people argue about. I've seen parents come into school, my previous school, when we had a maths fair, and I've seen parents shouting at each other about this. Is it better to switch? Is it better to stick? So here's my argument. The probability of winning by switching is 1 minus the probability of losing by switching. That's a fact of probability. And what's the probability you lose by switching? Well, that means you must have chosen the correct door in the first place, and then you moved away from it. The probability you choose the correct door in the first place is 1/3. So the answer is 2/3. So when I was talking to Vicky, I told her this, and this convinced me 100%, this argument. Because as a mathematician, I can follow its logic. It convinces me 100%. And it kind of convinced Vicky as well, but she still wanted to talk about it. And then I realised that I was a little bit reluctant to talk about it. Why should I talk about it? Because it's 100% true, my little mini proof. And then I thought, well, as a language teacher, Vicky's more used to acquiring knowledge through the way of knowing of language. And there's ways to talk about this problem and realize the structure of it and talk about the structure to see the underlying reasons behind the fact that you should always switch. But in mathematics, I guess we have a bias to look at the reasons, to use reason as a way of knowing. So I think it was an interesting contrast of learning styles, if you like. And I'm sure IB18, many of you have felt this at some point in your careers as a mathematician, the contrast between using language as a way of knowing and using pure reason. And of course, sometimes in maths you need diagrams to reach an understanding. You need some sense perception. And probability is a topic which relies heavily on diagrams, as we'll see. So, your teacher may have shown you a little bit of the history of this problem. It's a very famous problem, made famous by Marilyn Vos Savant, who became famous because of her answer to this problem, and also because she was or is in the Guinness Book of Records the woman with the highest ever recorded IQ. Your teacher may have shown you this document, which is on the student intranet site for TOK. 25 arguments for the Monty Hall problem. The first one, given by Marilyn in the pages of a magazine in the US, and then underneath some responses from highly qualified mathematicians telling her in no uncertain terms that she's wrong. What is it that teenagers say nowadays? Check yourself before you wreck yourself. Well, Marilyn had some very critical responses to her answer. Here's another example. But she was right, okay? She was right. One of the arguments that she put forward you can use this type of approach. I've shown you one, but here's another one. Is to increase the number of doors. So here we have 3 doors. If we increase that to many doors, and we have the same experiment, so I choose a door, and all the others are opened to show the pig, except one. Should I stick or switch? I switched. I won. I switched. I won. I switched. I won. I'm always winning by switching. There, I lost. It's not a guarantee. But if you think about it, by extending the problem, you can get a feeling for why it's better to switch. I'll leave you to think about that. But the argument for many doors is the same as the argument for 3 doors. Sometimes in maths, when we're trying to establish a truth and we're not sure, we can simply make the problem bigger and see if that helps.